Hello, this is my lab report for Lab 4, the physics of extreme sports with ropes. The objectives of this lab were to analyze and plot the motion and tracker of a weight oscillating at the end of a spring, to predict the motion based on a model in VPython, to compare the predicted motion with the analyzed motion, to graph the energy changes that are computed in the model, and to answer what if and what does it mean questions. To start, I analyzed a video of a weight swinging at the end of a spring. Here is the video and tracker. As you can see, the position of the mass was tracked, and the data, the position and the time, was graphed here, the x position and the y position. Using this data, I calculated some that will be used in the lab. One value, mass, was 0.02 kilograms, the relaxed length of this, which is 0.70 meters, the initial position, and g, which is the gravitational force. The values that needed to be found were the period of oscillations, the spring constant, and L0. To calculate the period of oscillations, I found the amount of time it took to make 3 complete oscillations and divided it by 3, giving me the average period of oscillations over that 3 times. I found that to be 1.647 seconds. I then used that and the already known mass to calculate the spring constant, or K, using this formula shown here. I found K to be 6.3799. I then used K and as well as the mass and the gravitational force to find, and the relaxed length of the spring, to find L0, which ended up being 0.0825 meters. The next step was to make a model in VPython. To do this, first I needed to insert the already known values and the already calculated values. Here I inserted the mass of the weight, the initial position, the initial velocity, and the time that it started. Over here I inserted the gravitational force, the spring constant, L0, and the equations needed to specify the spring force. Next, I needed to insert the energy principle into VPython. Here we can see the kinetic energy, the potential gravitational energy, and the potential spring energy. The kinetic energy formula is 1/2 mass times velocity squared, as shown in the code. The gravitational potential energy is mass times the gravitational force times h, the height or the position of the weight. The potential spring energy is 1/2 the spring constant, s squared. I then had to find the change in these energies, as shown in this part of the code right here. As you can see, the formulas for the kinetic energy, gravitational potential energy, and spring potential energy are still here, as well as an added line to find the change in each energy, which is just the energy minus the initial energy. Next, I needed to add lines of code to find the interactions on the weight. Here we needed to find the forces on the weight, which were the gravitational force and the spring force, which added up to be the net force, and use Newton's second law to find the new velocity and new position. Over here we needed to update the length of the spring so we could update the position of the spring. After adding all those lines of code, I ran my model and could get this. Two of the graphs I found were both of these. The first graph shows the analyzed motion versus the predicted motion. Ideally, these should be the same graph. However, based on an initial position error either in my CSV file or in the actual code itself they are not. However, they are very similar in shape, so I know that the forces acting on them and the change in energy are very similar. The second graph shows the energies of the system. The potential energy of the gravitational is in green, the spring potential energy is in red, and the kinetic potential energy is in blue. All of these added up should equal 0, and they do, which is shown in yellow, which is the total energies. Now to answer what does it mean and what if questions. For your model system, is the energy principle satisfied? As you could see in the last graph that I showed, the total energy change was equal to 0, which solidifies the energy principle. So yes, the energy principle is satisfied. The second one. Using the data you obtain in Tracker, make two separate estimates of the oscillation periods. First, by estimating the period of oscillation from the X position data, and second, by estimating the period of oscillation from the Y position data. Compare the two estimates and discuss. The period of oscillation I found when I used the Y position was 1.647 seconds. The period of oscillation I found when I used the X position was 1.52 seconds. These are very, very close, and I believe the only reason that they are different is because of a fallacy in actually tracking the motion, the center of mass of the weight in Tracker. Thank you for watching.